A very good afternoon to all of you. So today we are going to discuss, we are going to continue our discussion on state space model from differential equation. Once again, I would like to provide all of you a slight revision of what we have studied till now, why it is important. I had in the previous lecture discussed with you the formation of a state space model, why it is done, why it is important, okay, and the two methods from which the state space model can be obtained. One is the differential equation method that I am going to discuss here, and another is the state variable method. Yes, transformation model. Two models, okay. These are the two models through which the state space equation can be obtained. So let's consider a differential equation model. Take a simple case of an RLC circuit. I will be assuming that the RLC are connected in the series, the input voltage is the VIT, and the current flowing through the circuit is IT. Okay, I think I am quite clear till this point. Now there are two storage elements basically which are present in the circuit, and as I had already discussed with you that only the storage elements are the elements which can form the state variable. R cannot be a storage element. R is not a storage element, or in short I can say that this is a dissipative element. Okay, so I can very easily say that L and C are the state variable components. These will combine together to form the state variables. Okay, so the quantity that is varying with regard to L and C are, in L I can say that the current is varying, that is L di by dt, and in C I will straight away say C dV by dt, that is the voltage is varying. Okay, now have a look at this. So I will assign names to these particular voltages. That is, the output voltage will be given name VCT, and then I will apply the KVL, Kirchhoff's voltage law, around the loop. So Kirchhoff's voltage law will give us, have a look at this. This is it. VIT, okay, I will use this pointer. Okay, VIT minus IR minus LDI by dt minus CdV by dt, minus V0 should be equals to 0, and IT can be written as CdV by dt. I think now I am clear. Okay, and this is all that we have to discuss regarding the first equation. And the second thing is that the output voltage is nothing but equals to VCT. It means there is a direct relationship between the output and the state variable, that is the VCT and the IIT. The two state variables are IT and the VCT. So as I had already explained you that the first equation can be formed as VI of t equals to RIT plus LDI by dt plus VCT. Okay, from this I can, by taking RIT on the left hand side and VCT on the left hand side, we will get LDI by dt equals to RIT plus VCT minus VIT. Okay, we will take the negative signs, and then the voltage across the capacitor is nothing but Vc of t is 1 by C IT dt, integrating it. Okay, I think till this point is clear. Now I will differentiate the above equation. That is, the differential of this will be taken, and this differential will lead to dVc by dt equals to IT by C. Now What are the state vectors? Now look at this. The state vector are IT and VCT. Already I had discussed that the inductor current and the capacitor voltage are the state vector. We can easily get a differential state vector, that is x dot equals to di by dt dvc by dt. I think till this point it is quite clear. Okay, one more thing is that, can you visualize a compensator here? If you look at this, before moving further, I would like to shed some light on the compensator, that is lead lag compensators. Okay, RC is connected and it forms the lag compensator, and when R and C are in parallel and R is at the output, and that is a lead compensator. Okay, a lag compensator increases the steady state response, so obviously the bandwidth will decrease, the noise will decrease, the signal to noise ratio will also be decreasing. Okay, and further more things will happen. Now we can form this di by dt plus dvc by dt from the above equation. The coefficient of it is minus r by l, vct is 1 minus by l, and vit is L. Vit is the, so you can get this expression in the matrix form, and y is related to it vct, vi is related to y, v naught t is related to vct. That's for the 0 to 1 matrix. So I will define a, b, c, and thus the model is obtained, and d is here 0. Now we will consider a transfer function model. That is, a transfer function having constant numerator. Transfer function can have a constant numerator, and a transfer function can have a polynomial function of s in the denominator. So before going into this, I would like to shed some light on the state transition matrix. That you can obtain the state transition matrix by doing this. If Si minus A inverse is obtained by the transfer function model, then we will get Xs equals to Si minus A inverse P of Us, where Si minus A inverse is the state transition matrix. Okay, that can be simply obtained by putting the value of Xs from this equation to this, and Si minus A inverse P will form the transfer function plus D. Okay, so this is your state transition matrix, and I think the properties will be here. If I can, yes, these are its properties. That is phi t equals to E of AT, Laplace inverse Si minus A inverse. That the first property, that is very important, that if you keep t equals to 0, then obviously this matrix will become an identity matrix. Okay, it means the diagonal element will be 1 and the rest will be 0. Second thing is that if you take the inverse of this, then it will be simply obtained by replacing t by minus t, because you can see here, if you are emitting phi of minus t, then it will becomes E of minus t. Okay, this is the zero input response, that is for x naught. Yes, initial condition, zero input response. Here the zero state response is not taken. Yes, initial conditions there, then it will produce an output. Okay, are you getting it? Because even when the input is absent and still we are getting the output, it is the zero input response. Now moving on to the next property. It is very simple, that if you take e raised to power at and t replaced by t1 plus t2, then obviously it will become eat1 plus eat2, both multiplied. That is phi of t1 plus t2 is nothing but phi t1 into t2. After that, the properties are discussed. Then let's go to a problem. The problem is very simple. Simply we have kept this y by us equals to c, si minus a inverse into t. Then these terms will interchange, and this will become plus 1, this will be minus 1. Upon matrix multiplication, we obtain the transfer function. So that's all for this lecture. I will see you in the next lecture. Thank you.